All right, class, here we go. So we're talking about polyatomic ions today. Now, there's a bit of a twist with these guys. You got to do some memorizing. Not the whole table, the table below. That's crazy. How about the first three columns? The last two columns are more of a grade 11 chemistry thing, and we'll get into that. We can use it too, but it's not going to be required. So, polyatomic ions are ions where we have more than one atom making up a single particle. Let me back out and go to the rules. The name of the metallic cation goes first, is not changed. And then you just put the name of the non-metallic polyatomic or non-metallic polyatomic ion next. There's no "ide," it's just the name of the polyatomic ion. So sulfate or hydrogen sulfate or carbonate. We don't have to say carbide or sulfide. Those are for binaries, okay? So that's how that name code goes. So you need to know the name and the formula and how to do a simple particle, which is, well, simple, right? So let's rip through these dudes. So ammonium is a relative of ammonia, and its formula is NH4. And since it's nitrogen in it as its central atom, I'm going to use blue because that's the color code for nitrogen traditionally. And we just put a plus in there. Now, hydroxide is formed when a proton dissociates from water, and this is now what we call a basic ion. This is what is corrosive in things like Drano, and it has a charge of -1. Carbonate, which is a derivative of carbonic acid, is CO3 with a charge of -2. And since it's, well, carbon's black, when we make it from burning toast, I'm going to use black for that one. And hydrogen carbonate or bicarbonate is a cousin of that one. And both of these are derived from the oxy acid known as carbonic acid. And in fact, that's actually used as a buffer in our blood. It's what keeps our blood pH in check. These are really, really important ions. Sulfate is derivative of sulfuric acid, and that's found in battery acid. Now, sulfur, of course, we're utilizing that yellow, so -2 for that one. Bisulfate, similar nomenclature, or hydrogen sulfate, HSO4, negative. And again, with that sulfur as the central atom, we're going to honor it with a little bit of yellow there. And our little buddy nitrate, whoops, nitrate coming from nitric acid, which is quite corrosive. You don't want to touch that either. And it's got a charge of -1, so a minus with a circle. That's fine. Phosphate. All right, phosphate. Its formula is PO4 to the -3. So it's got three negatives. Phosphoric acid is H3PO4, and this is why phosphate is PO4 -3. Now, this one's important because it's derived from phosphoric acid, which there's plenty of in, cola that you enjoy. Fortunately, not many phosphoric acid molecules dissociate, and that's why it doesn't burn us. So we call that a weak acid. Chlorate comes from, well, chloric acid, not hydrochloric acid. That's stomach acid. That's different. And it's got a charge of -1. So we're going to go like that for a simple particle. And for phosphate, a -3 will do. And that's good enough. If we want to level up, well, we would use what we call a space fill. Now, we derive that from the Lewis structure. And you guys don't have to know how to draw these, but I'm going to draw them in for you anyways. We'll just rip through them a bit quicker here. And since they're ions, we always put a square bracket and put the charge in the plus section there, or sorry, in the exponent spot there. We got an oxygen covalently linked to a hydrogen, and it's going to have three pairs of valence electrons around it, and that's going to give it an overall charge. So as we know, oxygen gains one, so one of those electrons there is the one that's responsible for the negative. All right, check this out. We've got carbon in the middle and 3 oxygens around, so we're going to lay those guys out triangularly. Now, since 2 of them have negative charges, I'm going to actually draw them as little stars so they kind of jump out at you. Okay, so that one there is going to be where one of the negative charge comes from, and 1, 2, 3, 4, 5, and that little dude there is where the other one. This one doesn't carry a charge, and that's because it's double bonded. So that overall particle has now got a charge of -2. And its similar cousin, 3 oxygens, except this one's connected with a little hydrogen there. So 1, 2, 3, 4. That one's connected there. 1, 2, 3, 4, 5, 6. Okay, I'm just going to highlight that one so it stands out as that one that's causing the negative charge on this particle. And this is one particle, even though it's made of 1 hydrogen, 3 oxygens, and 1 carbon. And it has an overall charge of negative. Sulfate. Okay, so sulfur with 4 oxygens around it. And I think you're starting to hopefully see the pattern here. Okay, 2 of them are negatively charged. We'll just use these ones here. 1, 2, 3, 4, 5, 6, and I'll put a little tiny X there so it jumps out. These guys are double bonded like that. 1, 2, 3, 4, 5, 6. Throw a bracket around it. Oops, that one kind of, the bracket came in there a little too close. There we go. -2. All right. Similar situation, right? So bisulfate, bond, single bond, but attach a hydrogen there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm not even going to bother showing which electron's causing the overall negative charge on that thing. It's not really necessary. Nitrate, since we've got a central atom like that, we're going to draw the oxygens in a nice triangular pattern. And that's actually how they lay out in reality. It's got a charge of negative, so only one of these dudes is going to have a single bond. Throw a bracket around it and a negative. Phosphorus in the middle here with 4 oxygens. 1, 2, 1, 1, 1. Negatively charged, negatively charged, negatively charged. Do you have to know these or memorize these? No. No, simple particle, formula, and name that goes with it will do for this. But for those that are going on, this is important stuff to familiarize yourself with, okay? Will these ones be on the test or anything like Lewis dot of polyatomics? No, I'm not going to do that. It's grade 10. Cl with 1 negative charge, 3 oxygens, similar layout as nitrate. And technically, it could be any of those 3. It'd be the one carrying the negative charge. I just put them in the bottom right for whatever reason. Now, this is where the fun starts. We're going to draw what's called space fill. So this is where we get to doodle. So what I'm going to do is I'm going to draw a nitrogen atom there, nice blue one there, and I'm going to throw 4 hydrogens around that sucker. And anyway, one of them can carry that positive charge. Doesn't matter. Okay. Oxygen. Well, this is where the negative is, and the hydrogen here is actually just, not negative. It's just covalently linked. So that's that. All right, we got carbon in the middle, and that is black traditionally. And I'm just going to keep the layout similar. So that top one there is the oxygen that's not filled in, or that is filled in because it's not carrying a charge. And these two do carry a charge. What I like about drawing these when you're doing your compounds is that it again reminds you the difference between sulfide and sulfate. Right? By taking this extra step and drawing these space fills out, it slows you down a bit so that you can actually succeed in your answer. Sometimes you've got to slow down to speed up into our results. It's a paradox, right? I'm just going to color that carbon on top. That looks better there. There we go. Bring it forward a bit. Okay, so that's hydrogen carbonate, or bicarbonate as it's also known. So we got our sulfur in the middle here. And I'm hoping that you're drawing along with me, your paper. So follow along, draw along. Didn't tell you to do that, but shouldn't have to at this point. And these are the two that are negatively charged there. And this one's similar in structure. You got that sulfur in the middle, four oxygens around. Two of them are, these two are not charged. This one is, and then this one's not because it's sharing with the hydrogen there. Okay. So we can see if we went from hydrogen sulfate to just basic, just sulfate by itself, what's happened there is that oxygen's actually kicked that proton off and stolen its electron, and that's why it's got sulfate has -2. All right. Nitrate, here we go. Nitrogen in the middle, three oxygens around it. One, fill that guy in. Two, that one in. Three, good enough. Phosphate, right? So phosphorus in the middle, purple for phosphorus. Some conventions use orange. I like purple for it. Negative, negative, negative. There you go. Chlorine is a halogen, and they're traditionally drawn in green. I don't know why. Some super science nerd decided that, and everyone agreed. They didn't ask me. I guess I came to the game a little bit late. That's fine. And there you go. Now, again, with these guys, you can draw the negatively charged oxygens in any spot, just as long as you have the right number. Okay, so I'm going to run through a couple examples for practice so that you know what you're doing with homework. And again, we've gotten rid of the Lewis thought stuff. So we're just drawing simple particles. All right, so let's look at ammonium chlorate. Now, what's really cool is if I memorized it, I would just go ammonium. There it is there. And chlorate. Now, there's a bit of an issue here. First off, I can draw them close enough together to make it look like a compound. There we go. But prior to, I always ask you guys to show your work. So let's draw simple particles, right? So here's ammonium, and it's a negative, and here's a simple particle, chlorate, and it's a negative. So it's a 1-to-1 ratio, we can tell right away. NH4, ClO3. Okay, now if we were to draw these guys out in full, that would work too. I'm not going to do that with these guys. I'll do it with the other ones because it's just two. Now, there's a weird little rule here. Check this out. Brackets are required around all polyatomic ions except when there is only one of them. So subscript for these ions go after the closed bracket. And if you don't know what the closed bracket is, okay, the closed bracket is that bracket there, right? So if we look at magnesium, for example, maybe silver is not the right color for this bit. Let's do just closed bracket is this one right here. Okay, magnesium, I'm going to use for that, we use silver, and then hydroxide, we use red. Okay, now I'm going to draw hydroxide right out. So check it out. And G, a +2, sorry, simple particles. There we go. And we got hydroxide there. So I'm going to draw the whole hydroxide out just for fun. Yay, hydroxides. And it's take two hydroxides to make that magnesium happy. And that's why we put the bracket 2. So there's one that goes to that 2, and there's the other one that goes to that 2. So the 2, this little subscript here, that guy, is going to be the one that identifies that you've got two hydroxide ions present, right? Let's rip through a couple examples to set you off. Sorry, that was a little bouncy. Lithium phosphate. All right, well, we all know lithium. Lithium goes like that, and phosphate, not phosphide. Okay, so just to start off, to remind ourselves, sometimes, again, you got to write it out full first few times until you really lock it down. And I actually recommend that. Phosphate versus phosphide. Okay, so drawing these space fill ones out so that they've got every single atom for this purpose makes sense to me when we're just learning. Okay, it's like baby steps. So we can tell immediately that we need 3 lithiums to go with that one phosphate. So our formula then is Li3PO4. Now notice that we only have one phosphate, so we don't have to put brackets around it. And that was that first rule we were talking about. Now you could do it that way, or you could do it the super simple particle way. Either or is good. Again, I recommend for polyatomics to actually draw them all out. That's my professional recommendation. But if you're in a pinch, super simple particles will do. So we've got a +1 lithium and we got a -3 phosphate, which immediately shows us, yeah, we got to add in a couple more lithiums to Li3PO4. Let's take a look at calcium carbonate. All right, calcium's the metal, and calcium has a charge of +2. And carbonate, let's draw that sucker out just for good practice. To remind yourself that it's not carbide, has a charge of -2. There we go. Well, it's the simple 1-to-1 ratio. That was easy. Okay, so again, the super simple particle method would work too, but you lose that. You might mistake it as carbide, right? That's the only concern with going super simple on these guys and cutting that corner of the extra effort of drawing them up. Plus, it's more fun to doodle. I just find, right? So CaCO3, whoop, CaCO3, calcium carbonate, not calcium carbon trioxide, something like that. All right, so that's where the memorization comes in, that you'll remember that that's carbonate, and obviously that's calcium, and that's a polyatomic ion. They should be jumping out at you. Okay, and again, that takes practice with memorization, which is a fair bit of effort. So I want you to dive into that. Now we got ammonium sulfide. Here we go. Now we're going to bump into that bracketing rule. Okay, and again, I'm going to start off by drawing out the full size ones here, base fillers. And it doesn't matter, again, which hydrogen gets the positive. So there's an ammonium. And sulfide, well, sulfide's just sulfur by itself, if we recall. And it has a charge of -2. So that means that we're going to need to have 2 ammoniums to make that sulfate happy. And maybe this one turns, so its plus is on the bottom hydrogen. Doesn't matter. Okay. Again, or if you want to take the risky route and go, well, that we got 1 ammonium there and 1 sulfide there. But the thing when you do this is you might forget that that ammonium is a polyatomic ion. So again, before it serves to put in that extra effort when you're first learning it. It'll just help your brain recall it later. And again, fun doodling, right? So this would work too later. And technically, I won't mark them either way. I'll keep them the same either way. We'll call that showing your work, either or. I like to give you guys choice. Now, here's where we can't bend. We have 2 ammonium, so we have to put that whole thing into brackets. And then sulfide is just by itself. Okay. So just to reiterate, let's go over here. Do it just a bit smaller. Okay. This 2 is referring to the fact that we have 1, we have 2. Right. So I hope that makes sense. Now, what I'd like to do is maybe do a couple more practice ones with you. And again, show all your work. That means draw simple particle drawings. All right. Let's think about calcium phosphate. How about that one? Hmm. Now for this one, we'll again use +2 for calcium and phosphate, -3. And I'm just going to do these examples quick because I want to wrap things up. -3 and +2. And when you draw out your simple particles, you'll eventually start to realize like there's only so many combinations of ratios we can have, right? So this now is going to be Ca3PO4, but we have 2 PO4s, so we got to put those guys in a bracket like that. Okay. We could think of iron 3, carbonate. All right. Well, we know the carbonate is CO3 and iron is Fe, and we know that this is a charge of +3 each, and carbonates are -2s. I'm jumping ahead. So first step, whoops, first step. What's going on? Oh, that's silly. First step, draw the ion. So we're going to draw the iron ion. There you go. And we're going to draw carbonate, and then we're going to look at and add them until they balance out. So when you have this 3-2 split, you're always going to have 2 3s and 3 2s. There you go. So this gives us a formula of Fe, and then carbonate, 2, 3, like that. And it even does work for crisscross when you're doing charges like that. Okay, so that's how we roll. Okay. Let's do another one. Plumic sulfate. Okay, so if we're talking sulfate, we know that's a -2. If we're talking plumic, let's do gray for that because lead is kind of gray. Well, plumic tells us that's the +4. So that tells us that we need to get 2 sulfates to match up with that plumic one. So Pb SO4 2 1 2. And I did draw them simply just to save time in my little lesson here. Okay, so from here, you got the rules, you got this note, you filled it out in your binder, I'm sure. You have access to it now. And you have homework to fill out the polyatomic combinations. And remember, if we have, watch out for there's multivalent metals, okay? But for this one, only show the stock. You don't have to do classical. Fair? Fair. All right. This is Shrenik signing off. We'll see you on Friday.